Hello. Okay. Can I start? Okay, fine. Okay. Good evening, guys. So in the previous session, we couldn't complete the questions for the 2015 paper. So let's continue from that point, and we are going to solve 2016 after completing the 2015 paper. Okay. So in the previous class or in the previous session, we have done some problems. Yeah, these were the problems that we have done. If you haven't watched this, you can go to the previous video and watch them. The detailed solutions have been discussed. And now we'll be continuing from the point where we have left in the previous session. Okay, let me go to the point where we have stopped. All these things have been discussed in the previous session. You can go and watch the previous video. This is a continuous series of question and answers for the previous year ISRO papers. That too for manufacturing, and this is belonging to manufacturing, production, and industrial. Okay, so this is where we stopped. Yes. So let's continue. So let's read the question. What is given here? During orthogonal machining with a HSS high speed steel tool, the rake angle is 5 degrees. So let us write what is given in the next page. Okay. So given. What is given? Rake angle is 5 degrees and undeformed chip thickness is 0.25 mm and width of cut is 4 mm. So let's write what is given and then keep on going. Okay. So rake angle is denoted by alpha, that is 5 degrees, right? Okay. Then undeformed chip thickness is 0.25, that is uncut chip thickness, isn't it? So I can write T1 or people write TC also, right? It is 0.25 mm. Right. Next, width of cut is 4 mm. So width of cut is denoted by B. So it is 4 mm. Next, assuming the shear strength of work material is 350 Newton per mm square, shear strength is denoted by tau s. Is 350 Newton per mm square. Okay, that's it. I hope this is the one that has been given. Determine the cutting force and thrust force. Coefficient of friction also is given 5. Okay. Let me take mu is equal to 0.5. Right. With this given data, they are asking to determine the cutting and thrust force. So we have been asked for cutting force Fc is how much and thrust force Ft is how much. So we'll discuss this with a concept. Okay. So first we have to discuss this with respect to the merchant circle diagram. Okay. So let's first we'll draw the diagram and we'll just see what is cutting force and what is thrust force, how this cutting force and thrust force forces are coming, and what are the other forces that are there, which can be calculated, which can be measured. All these things are very important. So this will come from the merchant circle diagram in metal cutting. So let's draw that merchant circle diagram. Okay. So the merchant circle diagrams look something like this. Circle like this. So actually we have to make the forces, then we have to draw circle, but I'm drawing circle for the easiness. Okay. So just wait for 2 or some time so that you'll understand what I'm trying to do here. Okay. Let me erase this. Okay, and this is tool, cutting tool. Okay, and this is uncut chip thickness, and there is, this is chip. Okay, this chip. Okay, this is tool. And now this is your workpiece. I'm not drawing anything inside to make sure that you understand the diagram first. Okay. So this is tool. This is chip here. Whatever is coming out, this is chip here. Okay. And if you know, the tool will be moving in the left-hand side direction, right? So the cutting force will be towards this direction. Okay. FC. Let me write that. This is FC. Okay. This is FC. Right. And the perpendicular to the cutting force, there is thrust force, that is FT. This is FT. And the resultant, we'll draw it in a different color here. Let me take it. So this is the resultant. This resultant R. Okay. Let me take another color here. That is this. So if you take this line here, sorry, this line, right? The angle that is made here is what is called rake angle. Is alpha rake angle. Okay. So if you, because that is the angle between the perpendicular, that plane, whatever the, the plane that I'm showing with respect to the tool is your rake angle alpha. Okay, fine. Now, as I think I should draw this again because it should make sense. Okay, the circle should make sense. So let me do it like this. Let me do it like this. So this is some other line. So let me erase what happened. Okay, let me erase this and let me take another pen. So here I'm extending like this. It means that chip is flowing on the surface. This is rake face, right? So as chip is flowing, there is some kind of frictional force that is acting on the face. As force is vector, I'm placing it like this. The force is like this. The force is on the frictional force F is in this line. Okay. And perpendicular to frictional force, of course, there is a normal force N. Normal force N. This is perpendicular. And this is perpendicular for us. This is perpendicular. Okay. So let me write that normal force N here. That is N. Okay. And for FC and FT, the common thing is R, and for F and N also the common thing is R, in the sense like the resultant is R. And there is one more set, that is shear force and force perpendicular to the shear force. Let me take some other color. So if you see, this will be your shear plane like this. Right? So this is your shear force Fs, right? And this force, I'm just drawing it in some other, this thing like this. So this force, whatever you are seeing, is Fsn. Fsn is nothing but shear force perpendicular, force perpendicular to the shear force, or force acting normal to the shear force. Okay, so that is what are these things. So for green color, blue color, and purple color, all this, there are some couples, F and N, right? F, N are one couple, right? FT and CFC and FT are one couple, and FS and FSN are one couple. all these things are having same resultant. This is R, and this also is having a red color one. Okay, so that is what is important. Okay, fine. Now let's do this. So this is the merchant circle diagram, right? You already know. If you don't know also, please do revise this. Okay, so this is alpha, and if you go and see this angle here, this angle, the angle between the cutting plane and the shear force plane, and this is called phi. It is called phi. Okay, and if you have a coefficient of friction between the chip and the tool face, coefficient of friction between the chip and the tool face is 0.5 they've given. But there is this thing called beta. Beta is known as friction angle, right? Beta is friction angle, and it is tan beta, sorry, tan beta is mu, or mu is equal to tan beta, they say. If you want to calculate beta, you have to tan inverse of mu. Okay. Now with the information alpha, T, B, shear stress and mu, we should be able to find out this FC and FT. That is the question that has been given. For that, we need to have some understanding, right? Understanding between this merchant circle diagram. Okay. So I'm not going to derive it. If you're going to derive, it will take a longer time. You can take all the triangles. You can take this blue color triangle with red, green color triangle with red, and purple color triangle with red. All these three triangles you can take, and the common thing that all these three triangles are having is this radius when resultant force or diameter of circle, merchant circle. The resultant force is R. So I'm directly writing the relation. So hope you'll understand that. You can derive it easily. So the relation is this: R is equal to F by sine beta. How did I get? First, I'll tell this. Okay, I'll tell this, then the rest of that will do it. So if you take this triangle here, if you take this triangle here, for that we need to have some angles drawn. Okay, so let me do that for you. So if this is alpha, I can say this also is alpha. This, of course, it is alpha, and of course, beta is nothing but this. It is F by n, right? Mu is, of course, you know that mu is F by n, right? Right? Mu is F by n, so beta is this. As this is beta, I can say this is 90 minus beta. This is 90 minus beta. Okay, let me not clutter this. So, okay, I'll do one thing. I will write R here. Okay, and I will take here, this is 90 minus beta. If you see, this purple line and this dotted line are 90 degrees apart, and I want to find this angle here, and that angle is beta minus alpha. If you do the calculation, you'll get it. So I will write here uh, this angle, sorry, is 90 minus beta. You can do the calculation if you want. So the reflection is coming aside, right? So let me put the little downwards. So let me write that here FSN, and this is beta minus alpha. You get it. Okay, beta minus alpha. So if you take the triangle, this triangle, this triangle, this triangle, this triangle, you can easily say sine beta. Sine beta is F by R, right? Sine beta is F by R, isn't it? Opposite by hypotenuse. And cos beta is N by R. From here, I'll get R is equal to sine, R is equal to F by sine beta, and here also R is equal to N by sine beta. and of course these two are equal, right? That's why I'm writing r is equal to f by sine beta is equal to n by cos beta. This is from that blue color triangle, right? If I take the other triangles and do the same thing with the angles that are present in between, I'll be getting this equation. You can do the derivation. If you have any doubt, please let me know in the comment section. I'll be able to make some, send you some pick or maybe do something else. Okay. So the formula goes like this. It is Ft thrust force divided by sine beta minus alpha. You can remember this if you want, but I don't think you don't no need to remember. If you know the merchant circle diagram, easily you can derive it in very small amount of time. Right? This is this. Fsn is equal to sine phi plus beta minus alpha is equal to Fs by cos phi plus beta minus alpha. Right? Now, what are we asked? We are asked to solve for this and for this, right? So for that, something is required. So they have given this shear stress. So we are going to start from there, shear stress. So for that, you have to know what is the formula for shear stress. Actually, for shear stress will correspond to shear force. So shear force here, whatever you are seeing here is shear force. That shear force we will get from that shear stress value. Okay. So if you have shear stress formula, the formula, so that is, I'm not going to derive this again. So shear stress formula is shear force divided by, or shear force into sine phi divided by width of the chip into uncut chip thickness. That is what is the formula. Okay. So from here I can say that Fs is equal to, all right, in the below, because I'll use the space right hand side for some time. So Fs is equal to tau s into d width of chip into uncut chip thick or undergone chip thickness divided by sine phi. So if you want the relation, Fs is coming. But for Fs to calculate, we have to be given with tau s. Tau s is already here. This is tau s. Width, yes, width is given B. T1 also is there, but phi is not there. What is this phi? We have to find this phi. Okay. So to find that phi, we have a formula. If you you can use the merchant circle analysis, right? We can use another formula, right? Tan phi is equal to r cos alpha by 1 minus r sin alpha, right? But we have to have r. R is not given here, right? So we can use merchant's analysis. So according to merchant's analysis 2, merchant's analysis, there are merchant's analysis 1, merchant's analysis 2, and Lee and Schaffer analysis. Okay, so it is 2 phi is equal to uh, 90 plus alpha minus beta. This is what is the merchant's analysis. Merchant theory says. Okay, so we have phi. So we have to find phi. We have alpha and beta. From this we can find phi. Right? Alpha is already given, that is 5 degrees. Beta is tan inverse tan inverse mu. Mu is given 0.5. So let's find beta first. So beta is equal to tan inverse mu, and that is beta is equal to tan inverse 0.5, right? So beta is some, I got some 26.58 degree. Okay. Alpha is given, that is 5 degree. Let's do this. That's it. So 2 phi is equal to 90 plus alpha is 5 degree minus 26.58 something. Okay, so phi is you can do the calculation here and there. It will be coming around some 34.23 some degrees like that, approximate value. Okay, and this is phi. Once we have phi, Okay, let's not circulate or let's not box it. Once we have phi, what we can do, we can use this phi to calculate the Fs, right? Let's do the Fs. Fs is equal to, what is tau s here? Tau s is 350 per Newton per meter. So 350 Newton per mm square is nothing but 350 megapascal. Okay, 350 megapascal, but we'll put it in mm square only because here we can see this is 0.25 mm, this is 2.2 mm. So it will be cancelling it off. So don't worry about it. Don't need to convert anything. 350 into B. B is 4. T1 is 0.25. So 4 into 0.25 divided by sine phi. What is sine phi? Phi is 34.23 degree. Right? To calculate Fs, I got Fs as 622.367 newtons. Okay, I got something like this approximately. Okay, if you this is approximate value based on your calculations. Okay, you got Fs. Now you got Fs. I can find Ft and Fc easily because you have phi, you have beta, you have alpha. Relate any of these two. You can equate Ft and this. You can read this. You can equate these two, or you can equate these two. If you equate these two, you get Ft. If you equate these two, you'll get Fc. That's it. Simple. So let me equate Fc and Fs. Okay. Let me do that. So from previous equation, Fc by cos beta minus alpha, Fc by cos beta minus alpha is equal to Fs by cos phi plus beta minus alpha. Fs by cos phi plus beta minus alpha, right? So from here I can write as Fc is equal to Fs into cos beta minus alpha divided by cos phi plus beta minus alpha. Substitute all the values, we'll get the answer. What is Fs? 622.367. Okay, let me write in the next page. Next one. Oh, sorry. Let me use another slide. Let me use it here. So let me substitute. So Fc is equal to 622.367. 622.367 into cos beta minus alpha. Beta is 26.58 minus alpha is 5. Okay. Cos 26.58 minus 5 divided by cos 5 plus beta minus alpha. What is 5? 5 is 34.23. 34.23 plus beta is 26 minus alpha is 5. You do the calculation, you get around 1029.45 newtons, right? And the similar way, you can calculate Ft also by equating Ft by these two. You can equate these two. Ft by sine beta minus alpha is equal to Fs by cos phi plus beta minus alpha. So sine beta minus alpha is equal to Fs by cos phi plus beta minus alpha. Same thing, substitute. So I'll write the formula here. That is Ft is equal to Fs is 622. I can write from the previous. It's only there is a sign instead of cos. We have sign here. That's it. 367 into sine of 26.58. Same formula here. Instead of cos, I'm getting sine. That's it. Because see these two equations, same here cos is there, but here sine is there. That's why I'm writing directly. Okay, divided by cos 34.23 plus 26.58 minus 5. If you do the calculation, you get around 406.96 newtons. So this is the answer. This is the answer. So you can pick the right option. I think the option is 1029 and 1406, right? 1029 and 406. It is the first option. First option is correct. That's it. Finished. No? It's very simple. It's a lengthier one, and if calculator was not provided for this question, there is no point these guys giving the question in the examination. I don't know why they're giving it, because without calculator, see how intensive the calculation is. Sine, cos, 36.4, approximately value also you don't know, because the options are very pretty close, 1029, 10252, 1000, very pretty close. So this is not a typical ISRO question if the calculator was not provided at that time. If calculator was provided, then it is good, no problem. But without calculator, it's next to impossible in that time limit to calculate these things. Okay, fine. Anyways, it is given. Hope you have to go ahead and do if you have time. If you're good enough, good. Okay. Next, the thing is, these questions are wantingly put. I told you in the previous class also. Wantingly, they are placing these questions to make you waste the time. Please do not waste it. Go ahead with the questions which already you have known and which are very easy to answer. If time is left, then come back to these questions and solve. Good. Next. The figure shows the principle of. So this will be from the metrology and inspection chapter, right? The syllabus. So these are the hole gradings, number of hole gradings, and these are the hole tolerances and shaft tolerances. Okay. So if you take like this is shaft, this is hole, right? So sometimes this is hole grading and this is your shaft grading, right? So sometimes there is an interference here, and there is an interference. Okay, so this is shaft and this is hole. So this part only they are highlighting it. That is hole tolerance here, shaft tolerance here. So if hole tolerance is like this and shaft tolerance is like this is shaft, this is hole, shaft, then there is an interference. There is a clearance here, like that, right? You know all these things, right? So please do revise if you haven't gone through this chapter. It's very important. So you see, they're giving some kind of an assembly. See the shaft, that hole, the shaft tolerances are keeping on increasing here, right? And hole tolerances also have been arranged in a proper way here. And they are saying that there is some kind of, these are deviations. What this is upper deviation and this is the lower deviation they are talking about. Okay, this is upper deviation and this is the lower deviation. I'll tell you what is that. Maximum hole size minus maximum hole size minus the minimum shaft size is the upper deviation. Minimum hole size minus the maximum shaft size, it will be the lower deviation. We'll discuss all these things. So everything has been given here properly. Now they're asking whether what does this diagram shows, what principle it is explaining by this diagram. So let's go option by option and discuss and see what is the right option. Okay. First we'll go and see what is traceability. What is traceability? In methodology, traceability is nothing but it's like, I cannot define it. The concept is like how accurate and reliable the measurements that we are making. So we are talking about measurements. We are not talking about any tolerances here. Measurement will come when you're having some measurement equipment, some measurement device is there. When if there is any measurement device, right? If you want to understand how reliable that equipment is, see, you have manufactured some item. Let's say somebody told me that they told you to manufacture some billet of diameter, some 26.2, some plus or minus tolerance, some point 0.2. You made it right, but if your measurement device is wrong, if there is problem with the measurement device, it will show you wrong, right? Then you feel that you might have gone wrong, and in the inspection you will discard it, you will reject the sample. That is not good. So to understand whether the calibration, so you have to do calibration properly. A standard, what is calibration? First, before checking what you have manufactured, there are some standard specimens. Already the standard specimens are having some diameter, some fixed diameter, right? When you are measuring with your vernier caliper or screw gauge, obviously it has to give that D whatever the standard specimen is having. So that is what calibration is. You do the calibration first, and then you see that yes, the equipment that I'm measuring is perfect. Then only go to use that machine, that device for the product that we have or somebody have manufactured it. That is the standard. So traceability in metrology refers to some comparisons related to instruments of the measurements we are making. So this is known as traceability. So there is no relatability or there is no relation between traceability and the diagram that they are showing here. So that is a traceability. Okay. So traceability in a loose sense will belongs to some kind of measurement devices or the standard of the measurements device. Okay, that is very important. So obviously this is not right. And then we'll discuss what is interchangeability. What is interchangeability? So let us say I have some screws. I have some screw and nut. Screw and nut. There is a thread here. And of course there is a thread here. Right? There is a screw and nut. So obviously, if you are manufacturing some screws and nuts, thousands of parts will be manufactured. Thousands, sometimes even lakhs of screws and nuts have to be manufactured in the mass production level. But see, for this screw, there might be some kind of tolerance limit. For this screw nut, there will be some tolerance limit. If at all randomly you pick one screw here, one screw from the screw bag, there is some kind of a not bag. So this is some cartoon where screws are placed, and there is some cartoon where nuts are placed. Different places these have been manufactured. Right? Randomly you pick any screw, randomly you pick any nut, and if you are fitting it, and if you are there fitting properly, right? You take any time, any number of time, any number of screws. You take any nut, any times, and the what I say is that the components that are produced in different batches, different places, also will fit properly. That is called interchangeability. Okay, even though you're replacing, you're swapping, you do anything, it's called custom fitting. Okay, so it is the ability of component to be replaced by another without any customization required. Right? So here I don't see any customization. They are organized here, shaft tolerances. It's not discussing about the replacement and customization. It's talking about the hole tolerance and the shaft tolerance. So interchangeability also is not a right answer. Okay. Next we will discuss what is the matched fits. Okay. So here, if at all you are talking about some shaft and hole, this is, you might feel that this will be having right answer, but I'll tell you what is this. Okay, so it will match fits will tell about the level of tightness or looseness between two mating parts like shaft and hole. Okay, so whether it's a clearance fit or whether it is a this fit. So for that, no, they'll have some diagrams like this. If you see, they'll be having diagrams like this, and they will start some diagrams, right? That is what it's called matched fits. Okay, so this diagram will not show that, but you might think that this will be the answer. No, it is not the answer. This will talk about selective assembly. What is selective assembly? It's like you sort them first. Here, see, sorting has happened here. Properly sorting is happened. You sort them first, and then you take one by one and see who is having the closer tolerance according to the diagram or according to the part diagram they are given. Because in assembly only you will be seeing all this tolerance, and because it has to fit. Somebody has designed, somebody has manufactured. Assembly people has to go and fit it. If it is not fitting, either it is a mistake of designer or it is a mistake of the manufacturing person who has done it. Right? So the practice of sorting this into different sizes and groups, and then assembling the parts from these groups with the closest tolerances that is possible is called selective assembly. So according to this question, matched fits, you feel it might be right, but it is not, because matched fits will tell you the uh, uh, level of tightness and looseness, but selective assembly, there is some sorting happening. So that is the answer. But sorting is very important. That's the reason why this principle shows the this figure shows the principle of selective assembly. Hope I made things clear. Still, if you have any doubt, please do comment in the comment box. We'll be able to answer it. Good. Next. Next is, okay, again it is from metrology and inspection. A basic hole is one whose lower deviation is zero, upper deviation is zero, lower and upper deviations are zero, none of them. First, you have to understand what is lower deviation and what is upper deviation. For that, I have a diagram already kept for you, because I cannot draw all these diagrams, right? So, if you see, this is hole, this is shaft. So, I'll do one thing. Let me make this figure a little bigger so that I can explain it very nicely. See here. So this is hole, whatever is this. So this is, you see, this is the zero line. So let me draw the zero line with some red colors to identify what is zero line here. So this is the zero line here. Okay, that is the baseline. Actually, what is zero line is nothing but the dimension that is required. Okay, but if you see here, there is some gap between the, okay, so this is the lower limit of shaft. This is the lower limit of shaft. This is the lower limit of shaft, and this is the upper limit of shaft. Okay, maybe it is not visible. Let me take some other color. So yeah, this is the lower limit of shaft. This is the upper limit of shaft. Right. This is the lower limit of hole, upper limit of hole, lower limit of hole, upper limit of hole. Okay. Sorry, lower limit of hole, upper limit of hole. Okay. So now, if you see here, what is the system? There are some what you say, things that you have to understand. One is basic size. The zero line is called basic size. Even this is called as basic size. The zero line is called basic size. Somebody said that you manufacture for 30 mm. That is what is that basic size. It's a nominal diameter or nominal size of a shaft or hole, right? Then you have some actual size, that is like whatever you are measured. Then there is this zero line, right? So from that zero line, we'll be able to identify the positive and negative. Okay, so different things are there. Okay, so you have to know this terminology, because explaining this terminology in this one question will be covering total limits, fits, and tolerances. Okay, let's not do that. Hope you can go and revise what is basic size, what is actual size, what is zero line, right, and what is deviation. Deviation is nothing but the difference between the basic size and the actual size. Well, right here, deviation is the, okay, let me write some formulas here itself so that it will be good for you. It's kind of a revision for you. So deviation is nothing but difference between uh, actual size minus basic size. Actual is what you have measured, basic is what you are intending to have. Okay, and another thing is upper deviation. Upper deviation is nothing but the algebraic difference between maximum size and the basic size. So what they are saying is, for anything hole or shaft, you take the maximum size and the basic size. Okay, you see upper deviation. This is for I think you see this is the distance. This is the distance. This is the upper deviation for the hole, and this is the lower deviation for the hole. Upper deviation, what is the formula? The maximum size of hole. This is the maximum size of hole, obviously. This is the maximum size of hole, right? divide minus the basic size. Basic size is it will coincide with zero line. So I'll write difference between maximum size minus basic size. Basic size, and I'll write and basic size or zero line. Similar way, lower deviation is difference between minimum size and for anything minimum size and basic size. So this is the upper deviation here, and this is the lower deviation for hole. And for if you're seeing for the shaft, the lower deviation is the minimum size and basic size. What is the minimum size here? The minimum size of shaft is this, right? And that is the reason why this is your lower deviation, whatever you are seeing here, and upper deviation is this, whatever you are seeing here. Lower deviation, upper deviation. Maximum size of shaft minus the basic size. That's why they have written no maximum diameter, minimum diameter. That's it. Okay. So with this concept, let's go and attack the problem. Basic hole is one whose lower. Okay. Now there are two systems that you have to understand. Okay, there are two systems that you understand. One is hole system and shaft system, or hole basis system or shaft basis system. Well, let me draw that diagram. So in hole basis system, this is zero line. This is zero line. And if you take the hole is this, shaft is something here. You see, there is no deviation for hole, right? So this is hole basis system. Right? And similarly, if you have the zero line like this, and shaft is like this, there is no deviation for the shaft, right? And hole is something like this. Hole basis system. So these two are two separate things. This is shaft basis system. Very good. Now, what is the question they're asking? Basic hole is one whose lower deviation is zero. So they're asking basic hole. Basic hole is what? Basic means the basic dimension, basic size they're asking. So basic size will coincide with zero line. I told you already. Basic size. Right? Now they want basic hole size. So in which you can get basic hole size if these two systems are there, in which you can get basic hole size? Only in hole system, because here only one of the deviation, see upper deviation, lower deviation, one of the deviation is coinciding with the zero line. So you have to go for the whole system. But here upper deviation, lower deviation, both are there for whole. But here lower deviation is missing, right? So that's the thing. Okay. So you can see here the lower deviation is zero, and this is the upper deviation. Upper deviation. So they're saying that the basic hole is one whose lower deviation is zero. That is the answer I'm looking for. Hope you're getting it. Okay. So obviously upper deviation is not zero here, and lower and upper deviations are zero. No way you can see there is lower and upper deviation zero in any of these basis system. And it is an ideal case where uh, uh, this lower and upper deviations are zero. If lower and upper deviation zero, there won't be a tolerance at all. Okay, so the answer is lower deviation is zero. So here actually this is lower deviation, right? But that is zero, and that is zero. The base, the less, what do you say? the lower tolerance or the lower limit of hole is equal to your basic size. You will be able to find out the basic hole. That is what is that they're saying. Okay. Hopefully you understand this properly. Good. Next. They're asking, as per, again, this is from metrology inspection, as per IT5 standard tolerance unit, I is equal to. Actually, it is a basic formula that you have to remember, but yeah, it's easy to remember only. The formula is given by I is equal to 0.45, okay, into cube root of, okay, option is C actually. I'll tell you what is this. Cube root of D. There's a direct formula they're asking. You should remember this. There's no other way. Is D. And what is this D here? D is nothing but the geometric mean of two diameters. What are these two diameters? Two diameters are the nominal sizes for the ranges in the beginning and ending for the tolerance, for standard tolerance grading. IT tolerance, right? So now there are IT5. For IT5, what is IT5? It is some IT grade 1, 2, 3, 4, 5, 6. We have till 16. IT 1 to 16. IT, I think 0 also is there. IT 0, 1, IT 0, 0. So IT 1, IT 2, 3, 4, 5, 6, 7, 8, till 12. As you keep on increasing this IT grades, the tolerance limit is being increasing. So if you are in the lower number, then the tolerance is very low. High precision engineering is required. If the IT grade is increasing from 12, 13, 14, 15, 16, the tolerance limit is very high. So generally like casting, that kind of things where IT grades are very high. Okay. So there are grades of manufacturing. So there is some grade of manufacturing, right? Grades of manufacturing and some standard tolerance. That is IT. Standard tolerance is your IT. Right? So the grade is, let's say, some IT5, and your tolerance will be 7 into I, and I is being calculated from here, and D is this, that the nominal beginning and the end sizings. If you are going for IT 6, IT6 is 10I, 10 into I you have to calculate. If you are going for IT7, it is 69. Like that, you have so many, so on. IT8, you have 25I. IT9, you have 40I. IT16 is 1000I. Okay, like that, you have so many things. It's a simple formula. It won't even take 2 seconds to answer if you know the formula. If you do not know, there is no way you can answer this. Okay, you have to remember this formula. Good, remember it. Next. Circular shapes appear in this fashion when viewed at an angle other than 90 degree. Okay, they're asking if you have a circular object and you are not viewing perpendicular to the object, you're not viewing parallel to the object. Okay, what is viewing perpendicular? This is circle, but you are viewing on front. You are looking from top. Okay, if this is circle, you are looking from top. It look like this. If you're looking from this side, it will be a straight line, right? So they're asking if you are looking from different view other than 90, how does it look like? Simple figure I could come up with in the online is this. This is other than 90, no? Right? Whatever the angle is theta, this theta is not equal to 90. If this theta is not equal to 90, then it will look like an ellipse. Is it not looking like an ellipse? Yes, ellipse, right? Looking like ellipse. Looking like ellipse. So hence the answer is ellipse, elliptical. Simple question. It's a geometry. Simple common sense. Anybody can tell. Not mechanical engineering. Anybody can say this. Okay. Next. Drawing which shows the product with its components in their correct physical relationship is called. So they are saying that there are so many drawings in assembly line, especially in the assembly lines in the manufacturing plant. We have so many drawings: part drawing, late drawing, assembly drawing, fabrication drawing. All these things are having different things. But first we'll understand all the options and then we'll go for the question that he's asking and put the right option. Okay. So what is part drawing? Part drawing is nothing but it is detailed drawing of all the information of a single part. Right. Let's say if you have some bolt and nut, bolt, right? It's a single part. For that single part, you have to have some diagram. It includes all the shape. It should be circular shape. What is the the dimensions of that? Which material is that? Okay, what is required? I'll tell you here. Okay. So part drawing, I'll write here. Part drawing will detailed drawing of a part, single part. What is information that is there in that? Information like dimensions of that single part, shape of that part, right? Circular ellipse, all these things will be drawn in that. Material, what is the material? If it is mild steel, there are different materials that will be there, and some finishing details like what is the surface roughness. It will be given like this, right? There's some surface roughness. There's so many things. That is called part drawing. What he is asking here, a drawing which shows the product which with its components in their correct physical relationship. Here only we're talking about a single part. There are no different parts here. So part drawing is only one part. They're asking for different parts there. So in this drawing, what they're talking about will have so many parts, but part drawing will have only one part. So obviously this is not the option. Okay. Next is layout drawing. What is layout drawing? Layout drawing is a type of drawing that shows the you know uh, structure of facility. Okay, facility wise in the respect of facility of um, um, what do you say, the production. Okay, facility of production. Or I mean, I'm not telling it right, but facility of something. So the thing is that say nothing. So whenever you're doing some work, you want to be organized, right? So if you're doing some kind of work in your laptop, let's say you're making some PPT, right? So what you do, you open all the tools that are required for making a PPT. So like that, if you want to make some part, so in the facility, you make all these things in one place. In the sense, like if some common parts are sharing some common machinability, in the sense one machine is there and that machine is required for threading. So there are some few components where threading has to be done. So that machine is put. And now for that part, if some other thing is required, so it is like intersection of all the physical relationship between the what do you say, uh, different parts, right? But it's not talking about the component level. It's only about parts. Okay, fine. So, but so you might ask that this is the answer. No, it's not that. It's all about facility. It's not about the drawing of that components, right? Actually, assembly drawing is what these guys are talking about. Assembly drawings will talk about the parts which are having their physical relationship. Let's say it will say, okay, here there is some bolt, and that bolt has to go into the nut, right? The physical relationship will be easily mentioned in that assembly drawing. Okay, I think this is the answer. Okay, and what is fabrication drawing? Fabrication drawing is nothing but it's information about the fabrication is different from assembly. Fabrication is nothing but it provides some specific details about the manufacturing parts or fabricating parts, especially processing, which process it has to go, material that has to be used, dimensions it doesn't say anything about the the physical relationship between the parts. The physical relationship between the parts will be told by assembly drawing. Okay. Hope I'm not confusing you. So hope you understand that the main differences between part layout and assembly drawings. Okay. For this question, the appropriate option is assembly drawing. Okay. Next. Which one of the following is solid state joining process? Okay. So before discussing the join. So joining process are nothing but welding only. So in joining process only, we'll be discussing the welding. Okay. So what is, we'll discuss one by one. It is very easy to discuss. Okay. So sorry, gas tungsten arc welding. So what is this gas tungsten arc welding? So what is solid state in the same or when we'll go to the question. What is solid state? Solid state is nothing but where the while you're welding, there won't be any liquid or there won't be any gaseous form of the state. So only solid state will be there. Okay. So in gas tungsten arc welding, you have some tungsten electrode. You have some tungsten electrode, right? You have some tungsten electrode, and some arcing is happening here, and you have some workpiece, and this is getting melted. Melting is not solid. Melting is liquid. This is liquid, right? So obviously, tungsten arc welding, gas tungsten arc welding is not solid state welding. Resistance spot welding. Yesterday we have discussed resistance spot welding, where we have some, sheet like this, two sheets that have to be done, and there is some two electrodes that are coming, and then you are putting some force, waiting some time. There is some nugget formed. How this nugget is formed? Because of the joule heating. How this joule heat is coming? Because of the resistance between the two sheets, because of the air gap. So now here also there is some liquid that is being formed. There is no solid thing. So obviously this is also not solid state welding. Friction welding. How friction welding is done? So you have some kind of a CNC lathe, some machine, and you have put it your this thing, right? This is your fixture. You are putting it, and you are rotating with RPM. And there is another rod that you have to join, rod 1 and rod 2, and this is fixed. First what you do, you rotate it, and then when you're rotating it, you come and touch this with this. Because of the friction between this 1 and 2, there is some kind of a softening happening between 1 and 2. Okay. As this softening happening between 1 and 2, you will not wait till it is getting melted. Some semi-solid, even if it will be in solid state only. Once that is done, you'll stop the RPM, and then you'll apply some force and wait for some time. This 1 and 2 will be stuck like this. Some kind of flash is created, and this 1 and 2, rod 1 and rod 2 are stuck to each other in solid state itself. So that's why friction welding is known as solid state welding. And submerged arc welding is again a liquid state welding, where the arc is submerged on the flux. There is some flux powder that we put, and arc is submerged inside it. You can't see that arc, right? So it is submerged inside the flux, and that is why submerged arc welding also is not a solid state welding. It's a liquid state welding only. Hope I made the things clear. So that is how the what you say explanation goes by. Good. So I think this is the last question for 2015 paper in the manufacturing part. And now, give me 1 minute. I will shift my slides from. So this is last for 2015. Let's go to 2016 in a minute. Okay. Please wait. Yes. Now I think we are back, and we'll discuss the 2016 paper. Okay, this is 2016 paper from the manufacturing part. Okay, so I think we have some 8 questions. Hopefully, we'll complete in some time, and we'll close the session for today. And the next session will start 2017 paper. Okay, okay, let's proceed. When a material is strain hardened, then they're asking some options. its yield strength reduces and ductility increases. Its yield strength increases and ductility reduces. Both yield and strength ductility increases and reduces. So okay, fine. So let's not go by the option. Let's discuss what is this strain hardening and pick the right option. That's the best way of doing it. What is strain hardening? Why? When strain hardening will come? Strain hardening will come, or strain hardening is known as work hardening. Strain hardening is also known as cold working. Okay, there are so many names for it. Okay, right. What is that? Strain hardening also is known as work hardening, or sometimes it's also known as cold working. Why? I'll tell you why it's cold working also. I'll tell you. Okay. So this strain hardening is used for increasing the hardness and strength of the material by plastic deformation. Okay. And plastic deformation, as you know, it is not reversible. Till elastic limit only you can go back to the original position. In plastic zone, you cannot go back to the original position because it is already plastically deformed, right? And this plastic deformation is used for your metal forming. Complete plastic deformation theory is used to solve, or theory is used to understand the metal forming. Or metal forming uses the theory of metal plasticity. So let's see what's happening. So when you have some kind of material like this is your strain and this is your stress. Right? So let's take something. Let's say mild steel. You have till here it is elastic zone. Some elastic limit, and then some kind of lower yield point, then upper yield point, and then it will go and it will fracture here at some fracture point, right? So let's say this is still some kind of an elastic zone. This is your E. This is proportional limit, elastic limit, upper yield point, lower yield point. Like that, there are so many points you can discuss. This will be discussed in the strength of materials also. So the part till this thing is your elastic limit. This is your elastic zone. And this is your plastic zone. Okay. So here, if you see that the upper yield point is read, and then it is going to some plastic zone, and you here surprisingly what is happening as the deformation is increasing, the stress is increasing very highly. Okay. Stress is what? Stress is nothing but the resisting force per unit area. So resisting force is being increased. As you keep on pushing, resisting force. As you keep on increasing deformation, pushing or pulling, whatever it is, the resistant force is keeping on increasing with the appreciable amount of strain that is happening there. Excuse me. Okay. So, so this is called the strain hardening. Whatever this, when there is an strain happening, and when there is some kind of increase in stress, and this is called strain hardening. So this is called strain hardening. Because upon increasing strain, hardening is happening because of the increase in stress, increasing resisting force per unit area. Okay. So the material is strain hardening, or the yield strength is increasing. You can say something. It's like yield strength has been crossed, and plastic deformation is happening, right? So why this is happening? Why this is happening? Because in material science, you will be knowing about some dislocations, right? Dislocations. Some dislocations will be there in the material. Dislocations will be there in the material. Different types of dislocations have been discussed in the material science section, right? These dislocations, what will happen? There are some grain boundaries also. So in materials, there are some grain boundaries, and there are some dislocations. Like some dislocations will be there. As you are trying to load it by compression or maybe by tension, whatever it is, as you are trying this dislocation density, they'll be moving towards the grain boundary. They'll be moving towards the grain boundary. when they are entangled, when this entangling of grain boundary with these dislocations, that will make the material very strong, and that will oppose this movement, and that opposition is shown in this stress here, increase in stress here. Okay, and as you keep on increase the strain, again this is an no, opposition that is happening because of the entanglement of this dislocation that has generated, and dislocations that are intersecting with the grain boundaries, that is impeding the uh, flow of the material. That impeding flow of material is coming from the resistance because of the entanglement, right? So what I can say is that if you are trying to uh, strain harden, what happens? Your strength increases, or your resisting force is increasing because your strength is increasing. So your strength will increase because resisting force is increasing, strength is increasing, and of course ductility will decrease. What is ductility? What is ductility? Ductility is nothing but it's the ability of material to deform easily. But here it is not deforming, no? So that is the reason why ductility will reduce. So with this, I think we'll be able to answer this question. When a material is strain hardened, its yield strength reduces and ductility increases? Of course not. Yield strength increases and ductility reduces is right. This is the right answer. Both yield strength and ductility increases is a quite a strange phenomenon. It won't happen generally. And both yield strength and ductility reduces. Here also there is very some different phenomenon. But generally for normal materials, if you're strain hardening, yield strength will increase and ductility will reduce. Both are opposite in nature. Why yield strength is increasing? Because of the opposition. Who is opposing? The dislocation entanglements are opposing the movement of the strain. Okay, so that is the reason why material is strain hardened, yield strength will increase and ductility will reduce. That is the answer. Good. Next, the hole is specified like this, and a mating shaft has a clearance fit and minimum clearance of 0.02, and the tolerance on shaft is 0.30 mm, maximum clearance between the hole and thing. So again, in the previous section also, in the previous thing also we have discussed, right? They're saying that mating shaft has clearance fit with minimum clearance of 0.02 mm. Okay, so if at all we can say like this. So there is this hole, there is this shaft tolerance, this width of tolerance, this whatever I'm tying is width of tolerance, and they're saying that the mating shaft has a clearance fit with minimum clearance of 0.2. This is the minimum clearance, that is 0.02 mm, right? And the tolerance on shaft is 0.03, and maximum clearance between the hole and shaft. Simple question. The tolerance of shaft is how much? They're asking that the width has been given, this width has been given, that is what, 0.03 mm. Now they're asking the maximum clearance between the hole and the shaft. Okay, so for this you have to do some calculations which are very important, because it is a little confusing but it is easy. Okay, so what is this minimum clearance? So let me write some formula. Minimum clearance, minimum clearance. What is what? Please see here. So I will write in different thing also here. So this is the max dimension of shaft, max shaft. Sorry, maximum dimension of hole, not shaft. Maximum dimension of hole, and this is minimum dimension of hole, min hole, and this is maximum shaft, and this is minimum shaft. Now tell me what is clear minimum clearance, because how minimum clearance will come? You take the maximum shaft size and you take the minimum hole size, minimum clearance will come, right? So here the formula says it is nothing but minimum min hole, okay, minus, I mean, of course, size. Okay, give size. These are all size, minimum hole size, maximum hole size. Okay, minimum hole size minus maximum shaft size. Maximum shaft size. Okay, so you know the minimum clearance. You know the minimum hole. What you say? This is the minimum hole size. Okay, here. Okay. Here they have given the 50. Okay, this is important. I didn't see this. This is important. So from here, what I can say, a hole is specified. This is the hole as 5 plus something minus 0. The upper tolerance is this much and lower tolerance is this 0. Okay. So it means what? It means this is a whole basis system. This is a whole basis system. Right? It means that this is your zero line. That's it. Simple. If this is zero line, minimum hole size will be equal to your actual size here, right? So zero line, this is zero line. If it is zero line, this zero line, what is this? This is 50. Right? Here they have given 50 here. If this is 50, minimum hole size also is 50, right? This is also 50. Okay? So that's the reason why we can find out the maximum shaft size, right? So minimum clearance is 0.02, minimum hole size is 50, maximum shaft size we'll find out. Okay, so 0.02 from the previous formula is equal to 50 minus max shaft size. The max shaft size is equal to 50 minus 0.02, that is some 49.98 mm. Okay, now we are asking the maximum clearance between the hole and the shaft. Why we have found out this the uh, maximum shaft size? Because if you are not knowing the maximum shaft size, this is the maximum shaft size. Okay, so this is the end. We cannot find out the maximum clearance. That is the reason. Okay, so you know the tolerance of shaft is 0.03. Right? So now you found out that the maximum shaft size. Okay, that is what is this. You found out this. What is this value? That value is nothing but 49.98 mm. That is the maximum shaft. Okay. No. Wait. Yeah, it is 49.98 is the maximum shaft size, because from here you're coming here. And they're asking the maximum clearance between the hole and the shaft. Okay, what is the maximum clearance between the hole and shaft? Maximum clearance is this, the maximum hole size and the minimum shaft size. They're asking this. Okay, so you found out the maximum shaft size, but you have to find out the minimum hole size also. See, maximum hole size. Maximum hole size is nothing but 50 plus 0.5, because we can find out from here. So I can find out maximum hole size, nothing but from 5 we have plus, how much is this? Plus 0.05, and this is plus or minus, so whatever it is, 0 here, it is 0. So from here I can find out that maximum hole size is 50. But what is here? 5, 50. Okay, 50 plus 0.05 is 50 plus. Now they're asking this, the distance between this and this. That is the maximum clearance. maximum clearance, because if you select a shaft with minimal shaft size and a maximum hole size, you'll get maximum clearance. No, good. So I can write maximum clearance is equal to maximum hole size minus minimum shaft size. Minimum shaft size already we have found out. Maximum hole size also we have found out from the question. Right? So it is 50.05 minus this 49 point somewhere maximum shaft size. No, it is minimum shaft size. No, okay. Minimum shaft size is you have to okay. We didn't find minimum shaft size. Okay, minimum shaft size is maximum shaft size 49.98 minus the tolerance, that is 0.03, because this is the 49.99 49 point, this is 49.98 minus 0.03. You have to do that. 0.03, that is 49.95. I'll write 49.95 here, and the answer is some 0.49.95 minus this 0 point some 1 mm. Okay, so that is the answer, 0.1 mm. Okay, hope you understood this clearance and straps. So this is the max hole size, min hole size, min shaft size, maximum shaft size. That's it. Okay, so max shaft size and min shaft size. Okay, so like that we'll be able to find out the value that is asking. It is a little complicated, not complicated, little tricky. So do not make any mistake with the calculations. Okay, good. Next. Again, so in the previous paper also we have discussed one question from the Taylor's two-life equation. The same thing have been asked here. What is that? In a cutting operation, the cutting speed was reduced by 20%, and assuming n is equal to 0.5 and c is equal to 350, Taylor's equation, the increase in two-life is reducing 20%. That is what has been given. Simply, you know, this Taylor two-life equation is Vt power n is equal to constant. This is Taylor's two-life equation. Taylor's two-life equation, right? So we can, there are two conditions. Case one is some cutting speed. Case two, cutting speed reduced by 20%. So case one, V1, case two, V2 is cutting speed reduced by 20%. So V1 minus 20%. So what is that? So it is 1 minus 0.2, that is 0.8 V1. That's it. Reduced, no? So now they're asking what is the change, what is the increase or decrease in tool life. Obviously, if you're reducing cutting speed, your tool life will increase. That is known fact, right? So I can say here some T1 and T2. They're trying to find out what is the percentage in increase in T1 and T2. Okay. So increase in tool life, increase in tool life, or increase or decrease in tool life will give you by this formula. What is the formula? T2 minus T1 divided by compared with T1. That's it. They're asking how much is this. Let's do that. So we can write V1 T1 power n is equal to V2 T2 power n. Right? V1 is V1, T1 is T1, n. What is the value of n here? They given 0.5. Okay, 0.5 is given. Okay, let's use that 0.5 is equal to V2 is 0.8 V1. We have already seen reduced velocity, right? So 0.8 V1, T1, sorry, T2 to the power of 0.5. So here they have given C value. There is no need of the C value. Okay. So here V1 gets cancelled. and I can write here as T1 divided by T2 to the power of zero point 0.5 is equal to 0.8. What we want? We want T2 by T1. Okay, we can write, we want this. Okay, I'll write it from other side. We want T2 by T1, T2 minus T1 by T1. What is this? T2 by T1 minus T1 by T1, 1. We have to find out this. So here it is reverse. So we will flip it. This is T2 by T1 to the power of zero point 0.5 is equal to 1 by 0.8. So T2 by T1 is equal to 1 by 0.8 to the power of 1 by 0.5. 1 by 0.5 is 2. You can do this. Uh, you'll get around some 1.56. Okay. So here we can say T2 minus T1 increase in 2 life is 1.56 minus 1 is equal to 0.56. So if you are multiplying with 100 into 100 into 100 you do into 100 into 100 is equal to 56%. Answer is approximately 56%. Interesting. Simple question. Very simple question. Okay. If you are fast in calculation, it won't take much time. 1 minute is less than 1 minute. You can do it. Next. Mass production of seamless tubes is done by the process. Okay, is done by the process. So we'll discuss different process here, and then you should be able to. What is seamless tubes? Seamless tubes are continuous tubes. Continuous tubes. There is no patch in between. Continuous tubes. Seamless tubes. Okay. So what is rolling? Rolling is nothing but I have some diagrams for you. Okay, I think uh, I did not place the diagram. Give me 1 minute. I will take the diagrams for you and see. 1 minute. I don't have diagrams, huh? But I made one diagram. Okay, and these are the questions. Okay, okay. Let me check. Please give me 1 minute. Let me check. Yes, I think. Please be patient. I'm sorry for this. You can skip this part. I will just trying to get the figures. I thought that I made the figure, but let me do that and paste it here so that it will be good for you. Okay. Okay. Let me get the figures so that will be without me trying. You can visualize it properly. Okay. Next is, I think we are done. Let's proceed. Yeah, I'm sorry for this interruption. So let's proceed from where we have stopped. Okay. So I'm talking about these figures. Okay, these figures will make you better understand what I'm trying to say. Okay. So the mass production of seamless tubes is by the process of. So this is rolling. Okay. This is rolling. Okay. So you can see rolling can be used for making some kind of flat sheets. It's there where there is a minimal chance that it's typical. In general, it is not used typical. Yeah, we can make if you want. We can make, that is different. But typically, this rolling is used for making flat and long sheets. Okay, flat and long sheets, long sheets of plates. Spinning is this. What is the spinning? It is like some kind of rotation is happening, and this is some kind of a mandrel, or maybe you can say this is some kind of a rounded tool. You can see this one, and you're pushing it inside it, so that there is some kind of a asymmetrical asymmetry is coming here, right? This is what is this? So this is metal spinning. So this also is generally is not used for making seamless tubes. Okay, and welding. So this is spinning, metal spinning, and this is welding. By welding, you can see these are seams. These are seams. I'll just say this, and these are seams. So again, there's a gap between that. But here, if you see, this is extrusion. Directly extrude how much you want. You can extrude. Long extrusion can happen, and these are your pipes, kind of thing, pipes, and this is your ram you're pushing through, and this is your die, right? And this is your material, right? So extrusion is the one where we can make, or where we can use this procedure or process for making the seamless tubes. Hence the answer is D, extrusion. So that's why I took these figures, so that you better understand why this seamless pipes are very better manufactured by using extrusion. Okay, next. Misran is a casting defect which occurs due to. So there are so many casting defects. We'll discuss them and we'll come back. What is misran? Okay. So of course this is misran. You see there is some mold cavity. Some liquid metal is going inside. Before reaching the farthest end here, it got, okay. Let me see. I'll show you this thing. Before reaching the farthest end here, it got freezed. Okay, so why it got freezed? Because maybe the temperature of the liquid metal is not high, so that by the time it has reached the end point, it got freezed, got the solidified, right? So because of insufficient fluidity, because fluidity was not there, because it didn't reach, suddenly it got solidified. If at all your fluidity would have been good, or the temperature of liquid metal is good enough, then this would have not happened. Especially if the fluidity is not there, it is slowly going. Okay, and next is cold shut. Cold shut also is like that only. You see here, there is unfusing. This you may I think I should zoom. So there is fusing that is happening. So here we are pouring. It is coming from here. It is coming. It is coming from here. It is coming. But there is some no unfusion. I mean, there is no proper fusion between the two streams here. Left hand side, some stream is coming. The right hand side, some streaming is coming. Both streams are not getting fused properly because of insufficient fluidity. So I can say that misran and cold shut are happening, mist run and cold shut are happening because of insufficient fluidity. And there are some cold shots. These are the small porosity gaps. Microporosity, some air bubbles are floating inside. Shrinkage cavity is coming because of insufficient, because you did not design improper riser design. Improper riser design. Riser is not put properly, shrinkage has happened. Because you didn't take care of shrinkage allowances, right? Then there is liquid shrinkage, there is solid shrinkage, liquid shrinkage, and solidification shrinkage. There are so many shrinkages. So you did not design riser properly, shrinkage has come. Porosity because of insufficient permeability. Permeability is one of the reasons why the gases have not escaped outside. Because of that, no permeability. Right? Hot tears are because of your insufficient heat transfer, or maybe the uh, cooling thing that is not happening properly. Because of that, hot tears are happening. There are so many reasons for it. Like that, there are so many defects: sand blow, pinholes, small sand wash, scab, penetration. This is misalignment of cope and drag box. If you're not placing the core properly because of the buoyancy effect, there is a upward shift of the core, and you're, instead of coming your hole at center, it is floating up. Right, circle is coming here. The hole is coming here instead of at the center. Mold crack. There are so many defects. For every defect, there is a reason behind it. But for our question, now we can answer this question. Misrun is catching defect which occurs due to high pouring temperature? No. Absorption of gases? No. Insufficient fluidity is the answer. Insufficient fluidity will be the answer. Okay. Proper misalignment of mold shaft, mold flask will give you this thing. And in absorption of gases, if it's not happening properly, this porosity will come. Right? So that is the reason. So, but this misrun and cold shut is another one where insufficient fluidity also will come. Cold shut. Cold shut is nothing but there is no proper fusion between the two liquid metal streams. Okay, good. Next, what is the common surface hardening treatment in steel? So, what are the different heat treatments are there? Okay, let's discuss that. What are the different heat treatments are there? What you know of? You know, annealing is one of the first one you can discuss. Annealing. Next, you can say about normalizing. These are very common things. Annealing is slow cooling, normalizing is fast cooling. This is furnace cooled. Slow cooling. Slow cooling. And this is fast cooling. Air cooled. Ambient cooling. Next is hardening. This is what they're asking about hardening. In hardening, there are so many ways you can do the hardening. It's not nothing about infusing carbon into the material. How we are infusing carbon into the material is what is called hardening. So you can do it by nitriding, cyaniding, induction hardening, flame hardening, carburizing. There are so many things. But in the options, it has been given carburizing. Right? So here in this we can say so many things. Carburizing is there. What is carburizing? Carburizing is nothing but you uh, you put the material, whatever that the material that has to be surface hardened. You take that material, you put in some environment where uh, it is around 900 to some 1000 degrees centigrade, something like that. You put in that environment and allow some kind of a gas which is having carbon, like some chemicals like propane or all these things. Methane is very toxic. Okay, so propane, all these things. Okay, so you put that material in 900 to 1000 degrees centigrade environment in the gas environment or liquid environment, like methane or propane, whatever it is, and you allow it for some time so that the surface is getting absorbed. Right, if this is the material, the surface is getting absorbed by the carbon so that the hardening is happening. Right, Then after some time, you can wait for some furnace cooling, or maybe you can quench it because you want harden. So you don't wait for furnace cooling, you have to quench it immediately. You'll get the surface as hard. So surface will be very hard surface, and hard surface, and soft inner soft, inner is soft. So that is why you are doing this surface hardening. So by now you can understand surface hardening is happening because of carburizing, not tempering. Carburizing, not tempering. Tempering is not a surface hardening treatment. It is used some kind of increment. It is used to decrease the brittleness, something like that, or improve the toughness. Is like that. So tempering is not for surface hardening. Okay. And quenching also, it's also not for surface hardening. It's only uh, to some rapid cooling with water and oil. Some rapid cooling is happening. Because of that, total material will become harder. Okay, so that's not our answer. Carburizing is the answer. Okay, good. Next, which of the following order of crystal structure will match with metals: iron, copper, zinc, and the dot? So you have to remember this. It's a memory-based question. There is no other option. So if you go and see, and the previous class also we have this previous session also we have discussed. This is simple cubic, and this is your BCC, body-centered cubic, and this is your FCC, face-centered cubic. So I did not show the HCP, right? I did not show the HCP. HCP is hexagonal closed packing. HCP is hexagonal closed packing. Okay. So for BCC, what are the different materials that we have? BCC, you have to remember, BCC are generally brittle in nature. Generally brittle in nature. And FCC are generally ductile in nature because of its structure. Okay. So HCP is some different material, close packing. So what are the brittle materials that we can talk of? Maybe you can talk of some higher tungsten, tungsten. What is the example that they have given here? Iron. Okay. So I can say that even iron also is some kind of a brittle material. So because of the carbon content, right? So I can say some ferrite, right? Alpha. Yesterday we have seen perlite and all, right? All these things, gamma, delta ferrite, gamma ferrite, whatever it is, iron, right? Iron. So I can say some delta iron, gamma iron, right? So like this, there are so many materials. Ductile, there are so many materials like uh, uh, silver, silver, copper. Silver is Ag, right? Ag, silver, copper, right? Nickel, lead, PB lead. There are so many materials like that. For HCP, you have to remember there are something like magnesium, some cobalt, some zinc, titanium. All these things are HCP. Okay. So in this example, what are the order? Iron, of course, it is BCC. Iron is BCC. Copper is softer FCC. Zinc is HCP. So BCC, FCC, HCP. So this is the answer. Okay, that is memory based, but not exactly. You should know which is softer, which is brittle. That is also sufficient. You don't need to remember all the list that you need to know. Okay, good. Next. Okay, wow. The question is this. Uh, it's a lengthy question again. The resistance spot welding operation is performed on two pieces of thickness. Okay, let's write what is given. Thickness is 1.5 mm. Very good. And using 1200 amperes, current is 1002 ampere, 12,000 ampere, sorry, amperes, for duration of 0.2 seconds. So T is 0. Okay, I wrote thickness as like this. No. Okay, I'll write thickness here, TH. T is 0.2 seconds. Okay. The electrodes are 6 mm diameter. Diameter of electrodes are 6 mm. Okay, good. Resistance is 0.0001 ohms, 0001. R is 0001 ohms. Resulting nugget is 6 mm. Okay, nugget is diameter and thick. So it is cylindrical nugget. Cylindrical nugget of diameter and some height. What is its diameter? Is 6 mm in diameter. So dn is 6 mm. Hn is 2.5. Nugget is found in between two plates. Okay. Unit melting energy for metal is unit melting energy. Unit melting. That is what is for energy for 1 unit melting. For 1 unit melting is 12 joule per mm. 12 joule per mm. Okay. What is the portion of heat generated was used to form the welding? Okay, they're asking the heating efficiency. Okay, because you have provided some input and some energy has been used for making the you are used for making the that energy wanting will not completely go into this thing. Okay, so heat required will be the melting that is happening because of this nugget will be melting because the nugget, whatever the size of this nugget, is because of melting that has happened because of the input that you have given. But input and output will be different. That is what is there. Okay, so input is this energy of 1 unit melting is 12 joule per meeting. Okay, and what is input you have given? In what is heat generated? Heat is generated because of the I square RT, joule heating. Okay, so let's make some differentiation. I might be confusing you. I'll write like this. So is equal to I square RT, joule heating. So Hg is equal to I square RT. Okay, what is I? 12,000. R is 0001, 0. And T is 0. Simply calculate. Oh, this is I square. This square. Okay. If we calculate, we'll get some 2880 joules. Okay, 2880 joules. Okay, now is it right? Yeah, it will be right. Next is I did the calculation. Hopefully, it is right. Yeah, it should be right. Now, next is heat required for melting. Melting is cylindrical nugget. Cylindrical nugget. Okay, so what is the volume of nugget? Volume of nugget. Volume of nugget is equal to the cylinder, right? Pi by 4 dn square into hn. Isn't it? Yes. So it's nothing but pi by 4 into 6 square into 2.5. This is something around 70.68 mm square. Mm cube, sorry. So here they are saying that unit energy required for 1 unit. What is that? 1 unit energy of required for 12 joule per mm cube. So for 1 unit is required. Sorry. Wait. I'll make it more sensible. Right. So unit melting energy for metal is 12 joule per mm cube. Okay. So array, for 1 mm cube, it is 12 joules. For 76.68 mm cube, how many joules? That is what you have to calculate. So it is nothing but heat required for this thing is 70.68 into 12. So that is something around 848.2 joules. Okay, let me erase this so that you understand it here. Okay. So now what is so this much you're providing, this much only has been used. So what is the portion that are used? So portion of, what is that portion? What they're asking? Portion of heat generated used. Portion of heat generated used to form the weld. Portion of heat generated to form weld is heat required, heat required by heat generated. Heat required is 848.2. 848.2. Heat generated was 12. No, 2880. 2880. So into 100 you can do for the percentage, right? So it will be around 29.5. Something like this. Okay. Some 48 something will come, but anyway, right? Okay, 28.4 will go. Okay, fine. This is the answer. This is also lengthier. I'm telling you again, if there is no calculator provided, don't do it at the first. Go do it at the end of the paper. This is a very good question actually. So let's discuss this in detail. Okay. So a wire has a mass of, this is the mass, radius plus or minus this, and length plus or minus this. Okay. So this I can say delta m, change in mass. This is delta r, change in radius, and this is delta L, change in length. Maximum percentage error in the measurement of density is, so what is density? Density is mass into volume. Mass into volume. M is equal to mass, V is volume. So as it is, they're giving a radius and length. Obviously, it is a simple wire. Wire is some cylindrical in shape. So it is mass into volume is pi by 4 d square L. But they have given in radius. So let's do it in radius. It is pi r square L. Pi r square is area into length will give you volume. This is density. Now they're asking the maximum percentage error. So what is maximum percentage error? It is nothing but the change in density for the original density. That is what they wanted. Okay, the change in density by the original density will give you the error, or initial density minus final density, or final density minus initial density divided by the original density that you wanted to have. Right? So for that, we can just directly apply logarithm with both sides because they wanted delta p by p into 100. So that is what they want, is the question. So apply log on both sides. When you apply log on both sides, it is log rho is equal to log of m pi m into pi r square L. Let's go to next page. It is log rho is equal to log m plus log pi plus log r square plus log L. Right? Now differentiate this with respect to some quantity x, whatever it is, some quantity. Okay. So or differentiate on both sides, right? You can differentiate on both sides. If you do, it is 1 by rho, and differentiating this d rho will give you some. It should be d rho. I'm writing delta rho. Okay, d rho and delta rho. I'm just writing like this. D rho by rho is equal to d m by m. Sorry, I think I made a mistake here. Oh, mass by volume. No, yes. See, small silly mistake. Hurry only. This is by volume. By volume. So this will be negative of this. Hope you're understanding. It is okay. I'm sorry for this mess up. What a mistake I did. See, silly mistake. Mass into volume. How I wrote that? Silly of more. Okay. Minus pi RL. Because log A by B is log A minus log B. Okay. So this is this. This is this. This is this. Okay. Delta m minus log pi minus log r square. Okay, log pi differentiation is 0, no? There's no point writing it. It's a constant, right? It's a constant. Differentiation of constant is constant, okay, right? So this is 2 dr by uh, dr into r, right? I think it is 1 minute. 1 by 1 by r square into r cancels r. It's like r square and r will be there, r are cancelling, okay, that's it. Into dr will be there, dr by r I'm writing directly, minus dl by l. Okay, so this is assuming that your mass is increasing and radius and length, um, sorry, yeah, if radius and length are increasing, the mass will be increasing, and the error will be like this, propagating like this with respect to density. But here they're not asking about whether, they're not saying about whether wire is increasing or decreasing. They're on the both sides. They have increasing and decreasing, increasing and decreasing, increasing and decreasing. So they're asking a relative uncertainty, a relative percentage of the measurement, right? Maximum percentage of error. Error is what? Uncertain. We don't know anything about that, right? So as if you're putting the mass, radius and length increasing, then this will be right. But we are not having only increasing, we'll have decreasing. If you have decreasing, what will happen? This will be minus, this will be plus, this will be plus, right? So hence I can write in the scenario of relative changes or error propagation, this is very important. In case of relative changes or error propagation, actually we should write different. I mean, it should be like this is plus or minus, okay, because both sides we have propagation, error propagation. We can have plus sign when it is having positive change. We can have the negative sign. We have negative. We have when you have some negative changes. Okay. So if you are on the both sides of it, please you try to understand what I'm trying to say. The signs will depend upon the context in which the formula is being used, right? The negative signs when mass is increasing, the positive sign when the mass is reducing, but relatively both can be used, right? So to avoid the discrepancy, as we are not discussing about a single case, we are talking about the cumulative or relative uncertainty, right? So we are interested in the magnitude, so that's why we are putting positive. Okay, hence the formula changes to this. This is very important, very important. Plus 2 dr by r plus dl by. Okay, it's like, I mean, I'll tell you example. Let's say you have some water and you want to measure the saltiness. You're adding some salt in that, right? Then you taste it. So it will depend upon the quantity of water that is there and salt that is adding. That is the relative difference, right? So if you want to identify the percentage of error of saltiness, it can be on both. So you just see the relative change of water and relative change of saltiness. You just see into that, you'll get to the saltier, which is saltier, which is not saltier, like that you'll be able to get. Okay. So in mathematical terms, if you're dealing with some kind of uncertainties, absolute values are very important compared to the sign representativeness. Okay, so these are absolute values, very important. Hope I tried you to give a convincing answer. So then we'll go to the question. Now we have this thing. So we have delta M, delta R, and delta L. This is what? This is M. This is R, and this is your L. Simply substitute the values, you'll get the answer. That's it. Okay, let's substitute. So delta rho by rho is equal to delta M. What is delta M? Delta M is 0.003 by 0.3. 003 by 0.3 plus 2 into what is that? 0.005 by 0.5. 0.005 by 0.5 plus del L by L, that is 0.06 by 0.06 by 0.6 by 6, isn't it? 0.6, yeah. All are in grams, mm, centimeter, doesn't matter which dimension is it. So you will get something like 0.04 into 100. I'm doing it into 100 here, into 100, into 100 here, will give you some 4% of error. Relative percentage, very important. So that is what is 4% error can be there in the maximum 4% error can be there. Okay, combinations of this mass, radius, and length. Okay, so that is the answer. Yeah, that's it for today. So in the next session we're going to start the solutions for 2017. We have already completed 2015 and 16, and we can view these two videos. If you have any doubt, please do comment on the chat. I'll be able to respond. Thank you.